So after studying this module, you will be able to understand in detail the significance of unit root test in testing the stationarity of a series. You shall also be able to learn the augmented Dickey-Fuller test and its significance in analyzing the stationarity of a series. Also, another test which is used known as Phillips-Perron unit root test. And finally, we would learn the process of transforming the non-stationary time series into a stationary time series. So let us first try to understand what do we mean by unit root tests. Unit root test has become one of the most widely used methods for testing the stationarity of a series. So let us first discuss the unit root test briefly, and then we will proceed to its applicability in testing the stationarity of a series. Now, any series is generated by random walk if yt is equal to yt minus 1 plus ut, where ut is independently and identically distributed with mean 0 and constant variance. That is, what we are assuming is the error term is white noise. So we can write down that ut is distributed IID with 0 mean and sigma square as the variance, where IID stands for independently and identically distributed. In this expression, yt is the variable's value which is taken over the time t, ut is the error term, and therefore in general we can write down yt is equal to beta yt minus 1 plus ut. So if beta is equal to 1, we consider the model to be a random walk process which has an inherent feature of non-stationarity in it. You can see we are testing beta equal to 1, that is why we call it as a unit root. But we can also have a random walk with drift. So what is random walk with drift? On adding the drift variable in the random walk model, we get random walk with drift model, which is represented as follow. Yt is equal to delta plus yt minus 1 plus ut, where now delta is the drift variable. Similarly, we can define random walk with drift and trend, where a model which contains both the drift and the trend variable in the model, we term it as a random walk with drift and trend. So how do we write such an equation? Such an equation is written as yt is equal to delta plus yt minus 1 plus beta t plus ut, where beta is now the trend variable. So how do we test and how do we apply the Dickey-Fuller test? Let us try to learn in this segment. So to test the stationarity of a series, we assume our model to be yt equal to beta yt minus 1 plus ut. We take a null hypothesis which will further imply whether the model is a random walk process or not. As a result, our hypothesis will be as follows, which is null hypothesis H0 is equal to beta equal to 1. Similarly, we can write alternative hypothesis H1 to be beta less than 1. Now we test the model using a t-test and apply the following formula. So if we apply t-test, we can write down t equal to beta hat minus 1 upon standard error of beta hat. However, you will find that beta hat does not follow exactly t distribution. Rather, it follows a tau distribution. Therefore, to test the significance, we look at the table value of tau table rather than t table. So if the calculated value is less than the table tau value, then the null hypothesis is accepted and the series is a unit root random walk, and emphasize that if the series is a random walk or a unit root random walk, it is known as a non-stationary time series. So if the calculated value is greater than the tabulated tau value, then the null hypothesis is rejected, which implies that the series is stationary. However, the process can be tested using another method as well, where we can take our original model that is yt equal to beta yt minus 1 plus ut by subtracting yt minus 1 from both sides. So what would we obtain? We get yt minus 1 equal to beta yt minus 1 plus yt minus 1 plus ut. If you simplify this equation, we get delta yt equal to beta minus 1 yt minus 1 plus ut. Now, in this above equation, we can also rewrite it as delta yt equal to delta yt minus 1 plus ut, where delta on the right hand side could be written as first difference operator and is equal to beta minus 1. Now, before we proceed on to the testing procedure, it must be noted that if this delta is equal to 0, or which implies that beta is equal to 1, then this would imply that our model is a random walk process and hence is non-stationary. So keeping that in mind, basically we make the following hypothesis, which is, let me repeat again, h naught is equal to beta equal to 1, or it implies beta minus 1 is equal to 0 or delta equal to 0. And alternative hypothesis is that this delta is less than 0. Now we again test the model using the following formula, assuming that our beta follows a tau distribution. So we write t equal to delta hat upon standard error of delta hat. So this is distributed as tau distribution. Now summing up, if calculated value is less than the table value, then we accept the null hypothesis and reach a conclusion that the series is non-stationary. If the calculated value on the contrary is more than the table value, then we reject the null hypothesis and reach a conclusion that the series is stationary. Now we also have an augmented Dickey-Fuller test. This is another version of the test when mu t is not a white noise term, or the white noise term in different time periods are correlated with each other. Under these assumptions or under these circumstances, we use augmented Dickey-Fuller test. It is conducted by augmenting the following equations. The first equation is of a pure random walk where we have delta yt equal to delta yt minus 1 plus ut. Then we have random walk with a drift, which you know we wrote as delta yt equal to beta 1 plus delta yt minus 1 plus ut. Then we have random walk with drift and trend where we wrote it as delta yt is equal to beta 1 plus beta 2t plus delta yt minus 1 plus ut. The test can be applied in the form of above three equations. The first equation is of pure random walk method where we only consider a lag term. In the second equation, we add a lag term with a drift variable showing some kind of an autonomous change. In the last equation, we add the trend variable as well, showing the kind of a trend followed by the dependent variable taken into consideration. So in any of these equations, whichever we are using, we add lagged value of the dependent variable, which is nothing but, say, summation of delta yt minus 1, where summation of delta yt minus I, where I can take the value from 1 to m, which in true sense is augmentation. It makes the error term ut a white noise term. So when the error term is converted into white noise, then our equation becomes delta yt is equal to beta 1 plus beta 2t plus delta yt minus 1 plus summation alpha I into delta yt minus I, where I, as I mentioned earlier, takes the values from 1 to m, and the last term is plus ut, where ut is the pure white noise term. So we have delta yt equal to yt minus 1 and delta yt minus 1 is equal to yt minus 1 minus yt minus 2 and so on. Now, large number of lagged variables are included so that they are enough to make the error term serially uncorrelated. Under the Augmented Dickey-Fuller test, or also known as Augmented DF test, we assume the same hypothesis as mentioned earlier, which is that H naught now is that delta is equal to 0 and H1 is that delta is less than 0. We again use this following formula to estimate the calculated value, which is that T is equal to delta hat upon standard error of delta hat. But now it is distributed as Augmented Dickey-Fuller Todd distribution. Again, if the calculated value is less than the table value, we conclude that the error term is autocorrelated and hence the series is non-stationary. On the other hand, if the calculated value is more than the table value, we reject the null hypothesis, stating that the series is stationary in nature. Let us now move on to another test which is very important in our unit root testing, which is known as the Phillips-Perron unit root test. The test, as the name suggests, was invented by P.C.B. Phillips and P. Perron in their work Testing for a Unit Root in Time Series Regression in 1988. Now, Phillips-Perron test uses non-parametric statistical methods to avoid any serial correlation in the error term without adding the lagged difference terms as in the case of Augmented Dickey-Fuller test. I am sure you must have observed those terms there. So, what is the critique of the unit root test? Where is the need for a new test? The significance of the unit root test depends on the size and power of the test. By size, we mean the strength of the level of significance, or in other terms, the probability of committing the type 1 error. On the other hand, by the power of the test, we estimate the probability of rejecting the null hypothesis when it is false. So, before continuing further, let us take a look back at the types of errors which are committed in testing procedures. I am sure you know how we have seen that we can have type 1 error, type 2 errors. So, in this table, we have the first cell, which is of type 1 error, where the hypothesis is rejected when it is true, and we have the last column in a way, or last cell, where H is not is false. So, you look at this and you can see that what is type 1 error and what is type 2 error. Now, the power of a test can be calculated by subtracting the probability of type 2 error from 1, which means it is 1 minus type 2 error. And the maximum possible power can be equal to 1 if there is no type 2 error. So, what is the size of the test? 2.6.1 gives you the details about the size of this test. The Dickey-Fuller test is sensitive to the procedure of conducting it. If, for example, our true model is a random walk model, and however we estimate random walk with drift model, then the conclusions derived from it at 5% level of significance may be wrong. Now, this is because in the case of the latter, the true level of significance is much larger than 5%. Power of the test 2.6.2. Now, it is an inherent characteristic in the Dickey-Fuller test that they have a low power and tend to accept the null hypothesis more frequently than warranted, and thereby increasing the probability of committing type 2 error. The reasons can be attributed to the following. First, the power of a test depends more on the time span of the data as compared to the number of observations. For example, the power of a test would be more in case of 30 observations over 30 years as compared to 100 observations over 100 days. Second, if in a model, say yt is equal to beta yt minus 1 plus ut, and beta is approximately equal to 1 and not exactly equal to 1, then the unit root test would declare the model to be non-stationary. Third, the above mentioned models assume a single unit root, that is, the series is integrated of the order 1. If the model is integrated of the order higher than 1, then it may result in more than one unit root. In the latter case, we use Dickey-Fuller test. The fourth reason could be that the unit root tests are incapable of catching any structural breaks in the model. So how do we transform a non-stationary series into a stationary series? That is what we are going to learn in this third segment. So on regressing the time series which is non-stationary, we may incur a problem of spurious regression. That is why we have to convert a non-stationary series into a stationary series. So in order to avoid them, it is important to convert non-stationary time series into stationary time series. However, the conversion depends on whether this time series is difference stationary or trend stationary. That is what we have to first learn. Now, if you look at this chart, we are trying to show that you may have economic time series which may be difference stationary process or which may be a trend stationary process. In a difference stationary process, we have a stochastic trend, and a trend stationary process has a deterministic trend. So what is a difference stationary process? So if a time series contains a unit root, then the first difference of such time series will be stationary. Similarly, if the time series is integrated of higher order than 1, say I2, then we have to difference it twice. Let's estimate it using the following procedure. We take a variable y and observe its values over the period of time. The model will be represented as, again, yt is equal to yt minus 1 plus ut, where y is again the variable taken into consideration, t is the length of the time period, and ut is the error term as usual. So simplifying this equation, we may get yt minus 1 equal to ut. What we have done is only taken yt minus 1 to the left hand side. Now this can also be written as delta yt is equal to ut. Now any series generated by pure random walk is equal to white noise if it is a first difference equation. Now we use the Dickey-Fuller test to determine the stationarity of a series. A point to note is that the test in this case follows tau distribution, which we have emphasized. So please remember, it is tau distribution and not t distribution. Now using the Dickey-Fuller test, t can again be written as delta hat upon standard error of delta hat and is distributed as tau distribution. So we conclude by saying that if the calculated value is less than the table value, then we accept the null hypothesis and reach a conclusion that the series is non-stationary. If the calculated value is more than the table value, then we reject the null hypothesis and reach a conclusion that the series is stationary. So this may be a slight repetition, but I think it needs emphasis again and again. The second process is trend stationary process. The process states that any series which has a trend is a non-stationary series. We take the following model. Yt is equal to alpha plus beta t plus ut, which can be written as yt minus alpha minus beta t equal to ut. The model states that if from a series we subtract the trend, then the series becomes a stationary series. Here ut is a linearly detrended time series. Detrended means we have subtracted the trend from the original variable yt. Now it can also be possible that the trend may be non-linear in nature. For example, it could be that yt is equal to alpha plus beta 1t plus beta 2t square plus ut. Under this, the residuals will now be quadratically detrended time series. However, it should be noted that if a series is difference stationary process, but we treat it as trend stationary process, then it is called under differencing. On the other hand, if the series is a trend stationary process, but we treat it as difference stationary process, then it is called over differencing. So we have under differencing, or we may have over differencing also if we make some kind of errors. The specification errors created above can have serious consequences depending upon how one handles the properties of serial correlation of the resulting error terms. In general, most of the macroeconomic time series are difference stationary process rather than trend stationary process. So what have we learned so far? Let us summarize. This topic can be summarized as follows. A random walk model has an inherent characteristic of non-stationarity. A random walk model or a random walk model with drift model or random walk with drift and trend model, they all follow tau distribution. We have said that stationarity can be checked on the basis of whether the model has a unit root inherent in it or not. The other methods like Dickey-Fuller test and the Augmented Dickey-Fuller test can also be used for testing the stationarity of the series. The Phillips-Perron test uses the non-parametric statistical methods to avoid any serial correlation in the error term without adding the lagged difference term as in the case of Augmented Dickey-Fuller test. If the model is integrated of order higher than 1, then it may have more than one unit root, and in that case we use Dickey-Pentula test. We have also learned that an econometric or an economic time series is of two types. First, difference stationary, which follows a stochastic trend, and secondly, trend stationary, which follows a deterministic trend. We have also learned that if a series is difference stationary process, but we treat it as trend stationary process, then it is called under differencing. On the other hand, if the series is trend stationary process, but we treat it as difference stationary process, then it is called over differencing. Most of the macroeconomic time series, as mentioned earlier, are difference stationary process rather than trend stationary process.